to an atom, such as the proton, the neutron, and the electron. But in reality, there are dozens of other particles, each of them with a different behavior and each of them interacting differently with the others. One of the most fascinating particles is the neutrino. Neutrino is without a doubt the most elusive among the fundamental particles, since it barely interacts with matter and it requires gigantic detectors in order to be observed. Do you want to know more about neutrinos? Watch this video and I will tell you more. The discovery of neutrino is a very interesting story. At the beginning of the 20th century, scientists discovered radioactivity, atoms that spontaneously decay, turning into atoms of another element and emitting other particles in the process. One of these types of radioactive decays is known as beta decay. In this process, the nucleus of an atom emits an electron. The atom turns into one of another element. The reason for this change is that a neutron inside the nucleus turns into a proton. When scientists observed this process for the first time, they realized that there was something unexplained. In every physical process, energy is always conserved. This is one of the most important laws of physics, and there are no exceptions to it. However, the beta decay seemed to violate this law. In fact, when scientists measured the total energy of the recoiling nucleus and of the electron emitted in the decay, and they compared it with the total energy of the initial nucleus before the decay, they found out that the two measurements did not match. In every decay, there was always some missing energy. In the final state, the electron was always carrying away less energy than what was expected. The solution to this enigma was proposed in 1930 by the Austrian physicist Wolfgang Pauli, who had the right intuition. Pauli hypothesized that there was an invisible particle carrying away the missing energy. This particle must have been extremely elusive, since the detectors were not able to observe it. Scientists tried for decades to identify this particle, but Pauli's hypothesis was confirmed in 1956 only by Cowan and Friedrich Reines. Cowan and Reines realized an experiment to detect a special reaction known as inverse beta decay. In this process, a neutrino interacts with a proton in a nucleus. This proton then turns into a neutron, and a positron, the antiparticle of the electron, having its same mass, but opposite electrical charge, is emitted in the process. The positron then quickly interacts with the atoms around and turns into two gamma rays that are easily detectable. However, it was not that simple. In fact, the neutrino is the most elusive among all fundamental particles. Before explaining what it means, let me remind you that in nature, there exists only four fundamental forces. Two of them are very familiar to us: the gravitational force that acts between massive objects, and the electromagnetic force that acts between electrically charged objects. In addition, there are two more forces that act only within the microscopic world: the strong nuclear force, responsible for holding protons and neutrons together inside the nuclei of atoms, and the weak nuclear force, responsible for certain processes such as radioactive decays. In the microscopic world, the effect of gravity is totally negligible, because particles have super low masses. So, we can simplify the situation by saying that there are only three forces acting between fundamental particles: the electromagnetic force, the strong nuclear force, and the weak nuclear force. How easily a certain particle can be detected depends on how strongly it interacts with other particles, and this depends on how many forces the particle feels. Electrons, for instance, are easily detectable because they are electrically charged, so they feel the electromagnetic force. However, a neutrino has no electric charge, so it does not feel the electromagnetic force. To make things even more complicated, the neutrino does not feel the strong force either. So it interacts with other particles only through the weak nuclear force, which is the weakest of these three forces. Practically speaking, this means that neutrinos rarely interact with matter. To give you an idea, thousands of neutrinos pass through your body every second, without being stopped at all. They are even able to pass through the whole Earth and going out from the other side. Therefore, scientists need huge detectors in order to have some chances to observe one of these particles. The more material these detectors contain, the higher the probability of stopping and detecting one neutrino. To succeed in their mission, Cowan and Reines also needed a huge source of neutrinos in order to raise the chances of observing at least one of them. Initially, They thought that they could exploit an atomic bomb explosion for this purpose. In fact, an atomic bomb produces a huge amount of neutrinos alongside with other particles. However, since this idea was not very practical, they eventually decided to use a nuclear reactor as a source of neutrinos, luckily. Nuclear reactions do in fact produce many neutrinos, so this was the perfect source to use to identify the elusive particle. The detector used by Cowan and Reines consisted of 2 huge tanks of water. Most of the neutrinos produced in the nuclear reaction passed through the water tank, but a few of them hit molecules of water. When this happens, an inverse beta decay reaction occurs. The proton inside the water molecule captures the neutrino and turns into a neutron, emitting a positron as well. The positron then quickly disappears, producing 2 gamma rays that are easily detected. To make you understand how seldom neutrinos interact with matter, think about the following. The apparatus used by Cowan and Reines contained 200 liters of water. But despite this huge amount of water used, they were able to observe only 3 neutrinos per hour. For this experiment, Reines won the Nobel Prize almost 40 years later, in 1995. Unfortunately, Cowan was already dead by that time. But what makes neutrinos special is not only their capability of being so elusive, but also their unique ability of turning into another type of neutrino. This phenomenon is known as neutrino oscillation. What does it mean? Stick with me, and I will tell you in a few moments. Before talking about neutrino oscillations, we need to clarify an important concept. There are 3 types of neutrinos, not one only. Wait, what? We need to do a step back and talk about a certain class of fundamental particles called leptons. Leptons are those particles that do not feel the strong nuclear force. The electron is the most well-known particle belonging to this type. However, it is not the only one. There are 2 heavier versions of the electron, the muon and the tau. Both of them have same electric charge of the electron. However, they have larger masses. For instance, the mass of the muon is about 208 times larger than that of the electron, while the tau is even heavier. One of these 3 particles is associated with a specific type of neutrino, which are known as electron neutrino, muon neutrino, and tau neutrino, respectively. These 6 particles altogether are called leptons. To simplify, we can think leptons divided into 3 families, each of them having a lepton and its corresponding neutrino. The electron with the electron neutrino, the muon with the muon neutrino, and the tau with the tau neutrino. These particles always come in a pair within the corresponding family. For instance, when we talked about the beta decay earlier, we said that an electron is emitted alongside with a neutrino in the process. In that case, that was an electron neutrino. Another example is related to cosmic rays. And cosmic rays, which are essentially highly energetic protons coming from space, hit the atmosphere. They produce muons. And for each muon produced, there is also a muon neutrino alongside with it. Now that we have explained about the 3 different types of neutrinos, we can talk about neutrino oscillations. The first evidences of this phenomenon appeared in the 1960s, when the American chemist and physicist Ray Davis tried to measure the flux of electron neutrinos coming from the sun. Our star is a huge nuclear reactor where thousands of reactions of nuclear fusion occur every second, producing a large amount of neutrinos. These neutrinos travel all the way to the Earth, where we can detect them. This is exactly what Davis tried to do. Its apparatus consisted of an Olympic swimming pool located underground, in a gold mine in South Dakota, and filled with a dry cleaning fluid, able to maximize the probability of interaction of neutrinos. The experiment was located underground in order to minimize interference from cosmic rays. The fluid in the pool was rich in chlorine. When an electron neutrino hits an atom of chlorine, this turns into an atom of argon and emits an electron, which is then easily detectable. This process is known as neutrino capture. The results of this experiment were surprising. In fact, Davis observed only 1/3 of the number of electron neutrinos that was expected from the theory. Experiments and calculations were repeatedly checked, but no mistakes were found. Similar results were also obtained in other experiments, looking at the flux of the muon neutrinos from the atmosphere. As we said earlier, cosmic rays that interact with the atmosphere produce muons together with muon neutrinos. These experiments found out that the amount of muon neutrinos reaching the ground was less than what was expected from the theory. So, what was the explanation for these discrepancies? The answer is the neutrino oscillation. Neutrinos have this amazing ability of changing into another type. So, an electron neutrino can turn into a muon neutrino, or a muon neutrino can turn into a tau neutrino, and so on. Observing a neutrino oscillation is not that easy, because this transformation usually takes place over a large distance, so it cannot be contained within a single detector. The confirmation of this phenomenon came, however, in recent years, precisely in 2010, thanks to a joint experiment conducted by the CERN, the largest physics laboratory in the world, located in Geneva, Switzerland, and the INFN laboratory, located in Italy, under the Gran Sasso Mountain, approximately 700 kilometers from the CERN. In this experiment, a beam of muon neutrinos was produced by the LHC. The collider located under the CERN. This beam was pointed towards the Opera detector, located in the INFN laboratory, consisting of several meters of lead sheets interleaved with a special photographic films. When a tau neutrino interacts with an atom of lead, a tau particle is produced, and this can be observed with these special films. Between 2010 and 2015, 5 tau neutrinos were observed by Opera. Since the original beam produced from CERN contained no tau neutrinos, that meant that some muon neutrinos oscillated and turned into tau neutrinos along the way towards the INFN laboratory. This experiment finally provided the confirmation of this phenomenon that puzzled scientists for several decades. So this is all for today. By now, I hope you agree with me that neutrinos are among the most amazing particles. They are so elusive that can pass through everything, and they are even able to change identity through the oscillation phenomenon. Something is sure, no other particles can boast abilities like these in their curriculum. This video ends here. Thanks for watching, everyone.